Okay, so imagine this. You need to write, like, pretty sophisticated programs, but for devices smaller than your thumb.
Right, tiny things.
Yeah, with basically no memory, hardly any processing power. Think tiny sensors way out in the wilderness, maybe. Or critical control systems hidden away.
Places you definitely can't just pop out to fix easily.
Exactly. So how on earth do you make them do complex stuff reliably, efficiently, when they're running on, well, practically nothing?
It's a classic embedded systems headache, really. Your standard tools, even the smaller OS versions, they're often just too big, too hungry for these situations.
You've got maybe tens of kilobytes of memory, not gigs.
Precisely. Forget loading up Linux or your usual apps.
So that's what we're digging into today. We're looking at a really interesting way to tackle this. It involves taking a language you might know, Ruby,
Ruby, yeah.
but a version specifically shrunk down for these tiny spaces and combining it with a visual way of programming that's all about how data flows.
And the source for this is a great presentation by Kazuaki Tanaka from Kyushu Institute of Technology. He shared it via Ruby Kaigi, and it really lays out the problem and their solution quite clearly.
Yeah, it's fascinating stuff. So our mission here is to unpack how they're fitting these quite powerful programming ideas onto the smallest microcontrollers imaginable. And, why this actually matters for things like connected sensors, infrastructure monitoring, that kind of thing.
Absolutely. Let's get into it.
Okay, so first, setting the stage. Normal Ruby, the kind most people use, that's for what you might call rich environments, right?
Yeah, servers, PCs, places with plenty of memory, fast processors where, honestly, you don't obsess over every little bit of power.
Got power outlets nearby, no problem.
Exactly. But the focus here is totally different. It's small devices, IoT devices, where every kilobyte, every microamp counts.
And the researcher, Tanaka-san, his background seems spot on for this.
Oh, completely. His work covers things like machine learning for small OS environments, real-time operating systems, IoT systems in general, and, crucially, low-power wireless communication. He's deep in this world.
Okay, low power communication. That actually brings up a really concrete example from the presentation, doesn't it? LPWA.
Yes, low-power wide-area communication. They describe it as almost the opposite of 5G or 6G.
Opposite how?
Well, 5G is all about blazing speed, low latency, but maybe over shorter ranges.
Yeah.
LPWA flips that. It's very low speed. We're talking maybe 1 kilobit per second.
Wow, that's dial-up speed.
Pretty much. But the upside is incredibly low power consumption and really long range, like 15 or 20 kilometers from one little module.
Okay, so super slow, but it sips power and goes the distance. Why is that useful?
Well, it means it's low cost, the hardware's cheaper, and running it costs next to nothing in power. That makes it really attractive for, say, local governments. They might need to monitor large areas but don't have huge budgets for cellular plans everywhere or constant battery swaps.
Right. And the application they showed was using this for disaster prevention monitoring in Japan.
Exactly. With all the heavy rain, landslides, typhoons, earthquakes they face, getting timely data from remote spots is vital.
Makes sense. So what did the setup look like?
Pretty simple, really. A
Yeah.
small module, battery, maybe a little solar panel to keep it topped up,
Okay.
and connected to that sensors for things like rain intensity, wind speed, temperature, light,
Standard weather station type stuff?
kind of, yeah.
Yeah.
So the sensors collect data, the module bundles it up, and then uses that LPWA connection to send it back to the local government office.
Or the staff can see what's happening and decide if they need to, I don't know, issue warnings or take action.
Precisely. And the presentation mentioned this isn't just theoretical. They're doing this in places like Fukuoka, Fukushima, Miyagi prefectures.
So it's a real world need, and that need drives the requirement to actually program these old devices out in the field.
Exactly. You need logic on those notes.
Yeah.
Which brings us nicely to Rubik.
Right, the tiny Ruby, if standard Ruby is the full-featured beast.
Rubik is the bonsai version, maybe? It's specifically designed for these small microcontrollers or one-chip microcontrollers. That's where the CPU, memory, I/O, everything is integrated onto one tiny piece of silicon.
And the size difference is pretty staggering, isn't it?
Oh, hugely. Standard Ruby might need a megabyte, maybe more, of RAM. There's Ruby, which is smaller, maybe needs 120 KLP plus. But Ruby Kick is aiming for around 20 kilobytes, sometimes a bit more, but yeah, in that ballpark.
20 kilobytes, that's tiny. And you mentioned memory size is key for power. I thought it was mostly the CPU working hard that used power.
The CPU is definitely a big consumer when it's active. But the thing about memory, like SRAM or DRAM, is that it needs power constantly just to hold onto its data. even when the CPU is asleep.
Ah,
So if
figured.
you can drastically shrink the amount of memory you need, you drastically reduce that constant background power drain that directly translates to longer battery life. Months, maybe years out in the field.
That's a crucial point. So mruby is built for that. What kind of features does it offer in that tiny package?
Well, it gives you things you'd normally expect from an OS, but without needing a full OS.
Hmm.
It has its own built-in memory management, which is vital with so little RAM.
Right. No Malik headaches, hopefully.
Now, managed memory, yeah.
Yeah.
It also has power management controls, like the ability to put the CPU into that deep sleep state we talked about.
Okay.
And it offers semi-real-time processing capabilities.
Mm.
Not hard real-time like you might need for supercritical control, but good enough for many machinery or timing-sensitive tasks.
Got it. So how do you actually get your program onto the chip? You don't code on the microcontroller, right?
No, no. You write your Ruby or Ruby code on your development PC, like usual. Then you use a compiler to turn that into device-independent bytecode.
Device independent. So the same compiled code could run on different types of chips.
Potentially, yes.
Okay.
That bytecode file is then sent over to the microcontroller itself. Yeah. The microcontroller already has firmware loaded onto it, and that firmware is the Rubik virtual machine. Think of it like a tiny Java virtual machine, but for this Rubik bytecode. The VM executes your bytecode.
And how does it handle different hardware? Like talking to a specific sensor or blinking an LED on different boards, say an ESP32 versus something else?
That's the job of the hardware abstraction layer, the HAL. Rubik provides this layer. It's basically a set of libraries that know how to talk to the specific pins, timers, communication ports of a particular microcontroller.
So each type of chip needs its own HAL implementation.
Exactly. And these HALs are often shared maybe on GitHub, so if someone's done the work for an ESP32, you can likely use that, letting the same Rubik VM in your bytecode run on it.
Okay, so Rubik solves the language on tiny hardware problem. Minimal memory, minimal power, portable bytecode, that's one big piece. But then there's the logic itself. How do they make designing the program easier?
That's where the second part comes in. Data flow programming. Many people have probably seen visual programming tools, maybe in school.
Yeah, like Scratch, dragging blocks around.
Exactly. Block programming, Scratch, Blockly. There's even Small Ruby for Ruby itself. They're great for learning, visualizing logic. But the presentation points out a potential downside.
Which is?
For really complex programs, arranging hundreds of blocks can get, well, tedious. Students might actually find it easier to switch back to text coding eventually.
I can see that. So how is data flow different?
Data flow programming is also visual, using nodes and connections. But its focus is specifically on how data moves through the system. And this turns out to be a really natural fit for a lot of IoT applications.
Why is that?
Because think about what an IoT sensor node does. It senses something,
Gets a value.
processes that value somehow.
Checks if it's too high, maybe.
Right, and then acts on it. Sends a message, turns something on or off. It's a flow. Sense, process, act. Data moves from one stage to the next.
Okay, yeah, that makes sense. So you draw it like that.
Pretty much. You create a visual graph. You have nodes, which represent the processes like read temperature sensor, check threshold, send LPWA message.
Gotcha.
And you connect these nodes with wires showing the path the data takes. Data gets generated maybe by a timer node saying check every minute, or the sensor itself, and then it flows along the wires to the next node for processing.
That sounds like a really intuitive way to design the logic, especially for sensor stuff. But, okay, the big question. You draw this nice diagram on your computer. How does that diagram actually run on the tiny microcontroller with, like, 20 KB of RAM?
Ah, that's the clever integration bit. The tool they've built doesn't just let you draw the diagram. It uses that data flow description, the nodes, the wires, the settings, as the input to automatically generate the Rubik code or bytecode.
Whoa, okay, so the drawing is the source code, in a way.
Effectively, yes.
Yeah.
The tool analyzes your diagram, ignores all the purely visual stuff, like where exactly you place the node, its color. That's irrelevant for logic.
Right.
And it translates the actual connections and the functions of each node into working Rubik code.
That's really neat. The diagram compiles to Rubik, but how does that generated code actually manage the flow? On a single core chip, things only happen one at a time.
The core trick is a global queue. Think of it like a central message queue or a mailbox on the microcontroller.
Like you. Okay.
The generated code works in a cycle. First phase, data sources like a timer node or sensor input create little data packets and put them into this global queue. They in-queue them.
So data arrives, gets packaged up, waits its turn in the queue.
Exactly. Second phase, The main execution loop running on the chip constantly checks this queue. If there's a packet, it pulls it out, dequeues it.
Okay.
It looks inside the packet to see which node from your original diagram this data is for. Then it dispatches the packet to the bit of mruby code that implements that node's function.
Like the threshold check or whatever.
Right. And it executes that function using the data from the packet.
Hmm.
Maybe it toggles a value, does a calculation, or runs some custom Ruby snippet you define for that node. Then the loop goes back to check the queue again.
So this queue acts like a scheduler. It
Yeah.
takes events as they come in, lines them up, and the main loop just processes them one by one, executing the right bit of logic for each one based on the original diagram.
You got it. That queue-based dispatching is the heart of making the data flow model run on the simple hardware. And that blinking LED demo they showed, it looks super simple, but it illustrates this perfectly.
Yeah, the two LEDs blinking independently. One green, one red, different speeds, one every second, the other every 2.5 seconds. How does that work on one core?
Okay, so in the data flow diagram for that, you have two separate flows side by side.
Right.
Flow 1. A timer node set for 1-second intervals. It connects to a flip-flop node, which just toggles its output each time it gets triggered. That connects to the node that controls the green LED.
Makes sense. Blink green every second.
Flow 2. Another timer node, but set for 2.5-second intervals. Connects to its own flip-flop node, which connects to the node controlling the red LED.
Okay, blink red every 2.5 seconds. But still, how does the single core do both?
Because the generated Ruby code implements that queue system. The 1-second timer node just enqueues a packet for the green LED logic every second. The 2.5-second timer node enqueues a packet for the red LED logic every 2.5 seconds.
Ah, they just drop messages in the queue at their own rates.
Exactly. The main loop just picks up whatever's next in the queue. Maybe it gets a green packet, toggles the green LED. Then maybe later it gets a red packet, toggles the red LED. Then another green one. It just processes them as they appear in the queue.
Giving the illusion of running in parallel.
Precisely. And there's that sleep command they mentioned in the generated code. That's also key.
What does sleep do here? It's not just pausing, right?
No, not on these devices. When the Ruby code hits asleep, especially in the main loop when the queue might be empty, it tells the microcontroller's hardware to go into a deep sleep mode.
Low power state.
Extremely low power. The CPU basically shuts down most of itself.
Yeah.
It only wakes up when, say, a hardware timer interrupts fires, like the 1-second timer going off, or maybe another signal indicates there's something new to do, like a new packet just got enqueued.
Okay. So the chip spends most of its time asleep, saving power. It wakes briefly when a timer says, time to blink,
Yeah.
enqueues a packet, the loop processes it, maybe toggles the LED, checks the queue, finds it empty, and goes back to sleep.
That's exactly it. That mechanism gives you both the asynchronous style behavior, the LEDs blinking seemingly independently, and the low power consumption, all orchestrated by the code generated from that visual data flow diagram.
That is pretty clever, translating that visual flow into an efficient, event-driven, low-power loop.
It's a neat solution, and they're still working on it. The presentation mentioned ongoing efforts to improve the performance of that central dispatching mechanism. Makes sense if you want to handle faster data or more complex flows.
Yeah, you wouldn't want the queue backing up.
Right. They also talked about how this data flow idea connects to bigger pictures, like distributed systems, edge computing. You could imagine different nodes in a flow running on different devices.
Some on the sensor, some on a gateway, some in the cloud, maybe.
Potentially, yeah.
Mm.
Data flow models can sometimes scale like that. But then you hit another challenge they noted. How do you actually deploy your program easily and reliably across maybe hundreds of these little devices?
Yeah, managing a fleet of tiny things, that's a whole field in itself.
For sure. And it's clearly a team effort. They acknowledge the Rubik core team, the VM implementers, the local government folks helping with the real-world testing, and students and staff from Kyushu Tech and Matsu National College of Technology. Takes collaboration.
Absolutely. So let's try to wrap this up. What we've really seen in this deep dive is this combination, taking a language, Ruby, making it tiny and power-aware with Rubigic, and pairing it with an intuitive visual programming model, Dataflow, to let people build surprisingly complex but still very power-efficient applications for these incredibly resource-constrained devices.
Yeah, it's about bridging that gap, making it feasible to put sophisticated logic onto hardware that used to demand really low-level, painstaking coding while tackling those core issues of memory and power head-on.
So why should you, listening, care about this? Well, whether you're maybe tinkering with your own IoT ideas and want an easier way than embedded C, Or you're just curious about the tech inside all the smart sensors popping up everywhere. Or maybe you just find it fascinating how complex software can run on minimal hardware. This approach really opens doors. It could make programming hardware more visual, more accessible.
Definitely lowers the barrier to entry in some ways.
Right. Which leaves us with a final thought for you to chew on. If they can translate these visual data flow diagrams into efficient, low power code for tiny single chip computers like this, what other kinds of traditionally complex, maybe resource heavy programming tasks could we simplify or make more accessible just by rethinking the language and the way we actually design the logic?